This is run the gamut from, I have no clue, to come apart, I'm assuming to separate, to lose contact, I don't know. Things separating from one another, I might have known at one time, to split from, not sure, I don't know, to come apart. So, and my favorite here, to not associate with something. So, yeah, some good use of roots and suffixes and bases. To dissociate is to disassociate. So it literally refers to the process of something coming apart. You can dissociate yourself from a group of friends who you think are up to no good. You can dissociate, well, we're going to talk about what else you can dissociate in chemistry. How would you explain ionization? And a lot of you remembered back to like, something loses or gains electrons, you create an ion. I forget. Well, we actually haven't learned ionization in terms of solutions, so that's fine. I don't know. Formation of ions, adding an element, loss of a proton, something becoming an ion, taking or receiving ions, loses or gains electrons. How would you explain ionization? I wouldn't. Okay. Taking or receiving ions, I don't remember. Okay, what's the difference between net and gross? How many of you have received a paycheck in your lives? So have done work for money that wasn't like cash under the table for babysitting or mowing lawns. On your pay stub, you will see gross pay and net pay. Huh?
I wrote that my answer. I said, I know gross pay and I know net pay, but I don't know.
Well, okay. So a lot of you, I think only one or two people came up with net is part, gross is the total. Yeah, and you learned net pay and gross pay in finance. Actually, there is a comparison here. So I'm not sure. I don't know. Net is overall. Gross is how much in a time period. Not quite. I forget. No clue. Net gross is what's counted. Gross is what's predicted. I don't know. That's gross. Okay. So net, that was actually from a previous year. I scanned up and accidentally saw that. Gross is the total. So on your paycheck, your gross pay is the number of hours you worked times your hourly rate. So if you're making $10 an hour and you worked 10 hours, your gross pay is $100. Your net pay is after all your deductions come out, after your taxes come out, and if you're paying for health insurance, that comes out, and everything else. So your gross pay might be $100. Your net pay takes some things out, and you're left with your net. Make sense? Okay. What does it mean if something is an electrolyte? And actually, yes, somebody said, did Chapter 13 even happen? I don't know. We went through it too fast. That's true. We really hit the highlights in Chapter 13, so we didn't talk about electrolytic solutions except briefly. But we've talked about electrolytes before. We talked about them way back in Chapter 6 when we were talking about bond types. And we talked about ionic compounds and how they make electrolytic solutions. Remember I said you can stand in a bathtub full of distilled water in the middle of a lightning storm and shake your fist at a sky, you're just fine. Well, except the bathtub's metal, but maybe it's a fiberglass tub. I don't know. But pure water is not conductive. A lake or a river or an ocean is conductive. And it's those ionic compounds that are dissolved in it that make it conductive. And we call a conductive solution electrolytic. And I don't think somebody did mention Gatorade, able to conduct electricity. I know things can help restore lost electrolytes in the body. It's electrical, not sure. Has electricity. When electrolytes are dissolved in water, they break up into cations and anions. I should know this, but I don't. Don't know, don't quite remember. Okay. All right, good. So a few of you have sort of some memory of what electrolytes are, and I think the rest of you, as we're discussing it, is probably coming back. I'm seeing people go, oh, yeah. Oh, okay, that sounds familiar. That's fine. The road salt in the winter. So the second part of the title of this chapter is Colligative Properties. Salt changing the freezing point of water is a colligative property. We are, in the interest of time, pretty much going to entirely skip the colligative properties part of this chapter. It's good stuff. If you go on to college general chemistry, in most places you'll get some colligative properties work. But we're really going to focus on the ions in aqueous solution because that's the part that will help set you up to understand how acids work. And understanding acid-base chemistry is a whole lot more important than calculating how much the freezing point of water is going to change when you add salt to it. And by the way, that's what happens on roads, is when you add salt to water, you move the freezing point. Now, do you think you move the freezing point up or down? Down. And the water then has to be colder to freeze, so in essence what happens is we melt the water. We melt the ice that's on the roads. So it does melt ice, and it melts it because it changes the freezing point. So, but we're not going to do anything with colligative properties because just can't. So you guys were really good at using roots and suffixes to talk about dissociation. And this is what actually happens. When you take an ionic compound, and I just got rid of my baking soda solution today, when you take an ionic compound of any sort and you put it in water and it dissolves and it appears to go clear, what is really happening is that those ions are actually breaking apart. So remember, ionic compounds were really hard to melt. You couldn't melt salt at temperatures we can generate in the lab with a candle. They've got melting points up in the thousands of degrees. But man, you put them in water and they just let go. And that's because water is what kind of molecule? Water has areas of partial charge. It is a polar molecule. And those areas of charge basically are attractive to the ions. And this is an illustration I found years ago. So if we have sodium chloride, and remembering that sodium chloride is really a whole bunch of sodiums and chlorides all attracted to one another, all sort of holding hands because they are so darned attracted to one another. And they're attracted, whoops, I screwed that up. They're attracted because of their opposite charges. Well, the nice thing is that you can then get water, which of course, here's our little Mickey Mouse. And remember that Mickey's chin has a partial negative charge and the ears have partial positive charges. And what happens is these water molecules will sort of break up the party between the sodium and chlorine and in essence surround them because they're attractive too. They're also charged. And so what you end up with is sodium, whoops, let me get, that didn't work. You end up with sodium surrounded by water molecules with their little negative chins pointed in and their little negative ears pointed out. And I'm not doing nearly as good a job drawing this, I don't think, as the illustration that I found, but we'll have to make do. So they sort of gang up on and surround the sodiums like this. Well then, others of them turn those little positive ears to chlorine. And pretty soon what you have is a bunch of ions that are very neatly separated and surrounded by water. So now you have a bunch of ions that allow charge to travel because you have electrons that can move. And so we have an electrolytic compound, or an electrolytic solution rather. This process happens when you put pretty much any ionic compound into water. what you end up with is individual ions. So once you put salt into water, you no longer really have sodium chloride. What you have are sodium ions and chloride ions. And they're floating around on their own. The ocean is not salt water. It's a giant bath of ions. So in college, I had the opportunity, and if you ever get a chance as a science elective to take an oceanography course with somebody who's really good, do it. The guy I had was a former naval officer and a biologist, and he had a pretty cool perspective. And I hadn't really appreciated sort of the chemistry of the ocean before. It's just a giant bathtub full of these free-floating ions. Sodium ions, chloride ions, magnesium ions, calcium ions, potassium ions. A lot of the same ions. This is where it gets like all deep and cosmic and cool, and like you can go sit on the edge of the ocean if you have a chance to go sit at the edge of the ocean this summer and stick your toes in the water and think about the fact that the ions floating in the ocean's waters are many of the same ions that are floating in your blood. I like to just sit there and stare at the water. I don't get time to stare at the water anymore because I'm chasing now a 3-year-old to try to keep her from being eaten by a shark or pulled out to Europe. But if you have time to sit with your toes in the ocean and think about that, I feel it's a nice little connection. So anyway, when you stick an ionic compound in water, you no longer have that ionic compound in water. Stick sodium bicarbonate in water. Now you have sodium ions and you have bicarbonate ions. They're no longer holding hands. They've broken up. They have dissociated. This comes up to our first practice piece. We can write an equation for dissociation. And we're going to practice writing some of these. And it looks just like this. We show, well, there's one thing missing there. Can anybody tell me what I forgot to do? This should say solid. So we show a solid, there are two things actually that I don't have in there. We show solid sodium chloride dissociating. We typically put the H2O over the arrow to show that this is not a chemical reaction. This is dissociation, and it is different. There's no reaction happening. Notice that they're just breaking up. This is not a decomposition reaction, because if we dry this up, the sodium and the chloride are immediately going to hold hands again. They're going to reform. When we take 1 mole of sodium chloride, so 58.44 grams of sodium chloride, we're going to get out of that 1 mole of sodium ions and 1 mole of chlorine ions. So when we dissociate 1 mole of sodium chloride, how many total moles of ions do we get? 2. So we actually get more moles of ions than we had moles of the compound, because the compound has multiple things in it. We'll do a few together as practice, and then we'll look at 426 together. So if I give you 1 mole of calcium chloride. Calcium chloride is a pretty common ionic compound, and I tell you that this dissociates write the equation for it, the dissociation equation, and tell me how many moles of each ion you get out and how many total moles of ions. So I'll start out with the dissociation equation. We have solid calcium chloride, and we want to show that this is not a chemical reaction, this is just dissociation. What ions would calcium chloride break up into? This is where you have to also know your ions, just like you do for formula writing. Well, Ca2+, and that'll be an aqueous solution. And how many moles of chloride ions would we get? 2. We're going to get 2 moles of chloride ions, because if you notice, there's this little subscript here. So chlorine forms, I got to shrink this a little bit. Chlorine forms a minus 1 ion. And for every 1 calcium ion we have 2 chlorine ions. So we're going to get 2 chlorine ions, and those are also in aqueous solution. Does that make sense? So that subscript, anything that has a subscript like that, that's telling you that that ion, that there are 2 of this ion to 1 of that ion, that's going to end up becoming a coefficient. So stoichiometrically, I just love sneaking the word stoichiometry in anywhere I can. Stoichiometrically, how many moles of ions total do we get? 3. Because we have 1 mole of calcium ions, we have 2 moles of chloride ions. So we have a total of 3 moles of ions from this one dissociation. Let's practice another one. Let's make this one a little bit more interesting. We'll sweeten the pot. Well, let's not sweeten it that much just yet. So we have ammonium bromide. And we have 1 mole of ammonium bromide, and we're going to dissociate it. So how would we write the equation for that? Well, solid ammonium bromide dissociates in water. Nothing too terribly tricky about that one, is there? Other than the fact that I can't write aqueous to save my life. How many total moles of ions do you get out of that? 2. 2. So here's the tricky part. I guess there's a little bit of a tricky part. This ammonium ion, that doesn't break up. That ammonium ion is one thing. You're not looking at nitrogen and hydrogen ions separately. Remember that with your polyatomic ions, those things are covalently bound. You can't break up the ammonium ion without a chemical reaction. It's chemically bound. So you get 1 mole of ammonium ions and 1 mole of bromide ions. Does that make sense? 0 to 5. 0 is what is this? And okay. Let's do a couple more that get just a little bit more interesting, and then we're going to look at some compounds and predicting solubilities. Okay. What if I were to give you some solid calcium nitrate, and I told you that we were going to dissociate it? What would you get out of that? Whoops, I wasn't recording for any of that. Okay, so we got the 1 mole of calcium, 2 plus aqueous, 2 moles of nitrate, 1 minus aqueous. And the things to watch out for, of course, are remembering your subscripts end up being coefficients, and don't try to break up ions. Don't break up ions. Nobody likes an ion breaker. Okay, so now, would you believe me if I told you that you could predict if any compound was going to be soluble? So up to now, we've worked with solubility tables where you've said, okay, well, 42 grams of this will dissolve in this much water, and 178 grams of this will dissolve in this much water at this temperature. There you're actually looking at concentrations in solubility. How much stuff can you get in? Now, we just want to know if it's soluble or not, if any of it will dissolve. And the nice thing is that it's very predictable and it's very rule-based. So those of you who really like to know what the rules are and be able to follow a procedure and get an answer, you're going to like this. So if you would be so kind as to go to page 427 in the book. If you look at that chart on page 427, and I'll include a little picture of it here. Boy, is that handy. General solubility guidelines, and there are 6 rules. So when we're doing this, you look at compounds based on what's in them. So we talk about, compounds that have sodium, compounds that have a nitrate in them, compounds that are based on ammonium. And there are general guidelines with exceptions. So like if we look at the first rule, most compounds made of sodium, potassium, or ammonium are soluble in water. So if you have something that's a sodium compound, it's a pretty good bet it's soluble. If you have something that's a potassium compound, pretty good bet it's soluble. Ammonium compound, pretty good bet it's soluble. That one's pretty straightforward. There are no exceptions. The second one, most nitrates, acetates, and chlorates are soluble. Again, no exceptions. Okay. Number 3 is where we start to get into exceptions. So it says, most chloride compounds are soluble. Most chlorides are soluble, except silver chloride, mercury 1 chloride, and lead chloride. Lead 2 chloride, it specifies, is soluble in hot water. So it's not soluble in cold water. Remember, we had things that were also reactive in cold versus hot versus steam. Number 4 has some exceptions. Most sulfates are soluble except barium, strontium, and lead. 5, most carbonates, phosphates, and silicates are insoluble. So if you have anything that's a silicate compound, you're going to assume it's insoluble unless it's a sodium silicate or a potassium silicate or an ammonium silicate. And notice that that exception, that sodium, potassium, and ammonium, goes right back to the first rule saying, hey, most ammonium, potassium, and sodium compounds are soluble. Okay, most sulfides are insoluble except calcium, strontium, sodium, potassium, ammonium. So we're going to practice with these. Let's look at the first one. And what I'm going to ask you to do is jot down, is it soluble, yes or no, and which rule or rules inform your saying that. So, you could say this compound is insoluble, and I'm basing that on rule number 2. This compound is soluble, and I'm basing that on rule number 4. So, for ammonium nitrate, you want to try it, Caitlin? Soluble or insoluble?
Soluble.
Soluble. I like it. Yes, I agree. What are you basing that on?
Number 2.
Okay, so you're basing it on number 2 because this is a nitrate compound and most nitrates are soluble. That is true. This one also would be indicated that it's soluble based on rule number 1. So you can cite rule number 1 and 2 for this because it's not only an ammonium compound, which are mostly soluble, it's a nitrate compound, mostly soluble. Good. So yes, based on 1 and 2. All right. So how many of you got that right? Okay, good. And so you see it's pretty easy. You're breaking that down, looking at what pieces make it up. So for the next one, we have ammonium sulphide. I'll let you. Okay. So, and again, this is one where you can cite 2 rules, actually. You're correct. So ammonium sulphide is soluble. It's a yes. And that's based on rule number 6. Most sulfides are insoluble except ammonium sulphide. So really, you can base it on rule 1 and rule 6. You can say that it's part of the exception in rule 6, but looking at rule 1, we would assume it's soluble, unless there's an exception someplace else. Okay, anybody got the third one? Yes? Go for it.
I said yes.
Okay, based on which rules?
6.
Okay, hold on. So calcium carbonate is insoluble. So this is a no. Most carbonates, phosphates, and silicates are insoluble except sodium, potassium, and ammonium. This is not sodium carbonate, potassium carbonate, or ammonium carbonate. Do you know what calcium carbonate forms out in the world? It must be close to summer. I'm thinking beachy thoughts. Sea creature shells are largely calcium carbonate. So oysters and clams and bivalves, their shells are largely calcium carbonates. If calcium carbonate was soluble, the world would be a very difficult place for bivalves. Okay. Next one, silver chloride. So it's insoluble. This is another no. And it's based on Rule 3. And if you don't read Rule 3 all the way through, you might go, hey, most chlorides are soluble. Cool. Except, and this is one of those exceptions. So silver chloride is an exception. Mercury and lead chloride are also exceptions. Okay, and the last one. Anybody got that done? Want to try it? You want to try it, Destiny? Okay. Okay, so most sulfates are soluble. Good, you caught the except. And this is a barium sulfate. Most sulfates are soluble except those of barium, strontium, and lead. Okay? Pretty easy. I think it's much easier if you actually remember to cite the rule that you're using, because that forces you to really read the rule. I'm going to assign some practice on dissociation equations and predicting solubilities, and that's where we're going to stop today.